Our next speaker is Mr. Alan Wong. He's a senior staff yield management engineer at KLA Instruments. As a member of the yield management group, his responsibility is to provide KLA customers with yield management methods, technical resources, and leadership to help accelerate defect reduction and yield improvement rates. Prior to joining KLA, he worked as a parametric and wafer probe yield improvement engineer at Cypress Semiconductor and Paradigm Technology for years before moving to the Fairchild Research Center in National Semiconductor Corporation. At National, he developed a yield management system based on micro-yield modeling methodology that was later implemented at all of National's fab. He earned a BSEE from California Polytechnic State University and an MSEE from San Jose State University. So please welcome Mr. Wong.
Good afternoon. My name is Alan Wong. I'm from KLA Yield Management Group. Today, my talk would be a fast and effective parametric probe yield analysis methodology. Maybe this is one of the invisible defects, okay? Now, this is my outline of my talk for today. First, I will discuss a little bit the reasoning that I have to develop this fast and effective parametric analysis techniques. And later on, I will go to a little bit more details about this parametric analysis. Then I make some conclusion followed by question and answers. Now, the reason to require newer and faster parametric analysis is we want to understand the whole fab yield opportunities. As all we know, all the manufacturing defects that prevent the product being used 100%. So the manufacturing defect I'm talking about include the physical hard defects and parametric sensitivity, product design sensitivity, and that prevent the product die to be functioning. So it's very critical to identify both systematic and the random portion of the defect. What I define systematic defect is a defect that is non-randomly distributed across the wafer spatially. The random defect basically randomly distributed across the wafer spatially. The systematic could be caused by equipment, could be caused by parametric sensitivity, could be caused by product design. The random could be also caused by the equipment itself or the process-induced defect. Now, so the parametric sensitivity is definitely one of the source of the one of the defect source. So in a process, a set of parametric test structure is usually fabricated with the product die in itself. So those parametric test structures, usually people refer to as E-test structures. So at the end of the process, all those ET parameters is being tested, and the information from those ET structures can feed important information to the process engineer or device engineer to figure out what is the problem for the process. So to reduce the process defect, it's very important to separate and quantify systematic and random defect losses. The second reason is, as all the speakers talking about, we need a fast analysis to drive quick result. So the conventional analysis is usually doing is wafer to wafer level, yield to each parameter, E-test parameter to do correlations. As we all know, is over 100 parametric parameters in the fab being tested is very, is not uncommon. So if you're doing one-by-one correlation, it takes a lot of time. So somehow you need to automate the process to find out which critical ET parameter to have a significant yield impact. The last one is we also want to draw some statistical valid conclusion, not based on the one lot or few wafer. So we need to amass around the data to make statistical conclusions. Next, please. Now here's overall the parametric and probe yield analysis methodology. So it includes multiple die analysis, spatial distribution analysis, statistical correlation analysis, multiple regression modeling, and parametric process module analysis, and finally, generate of systematic yield improvement plan. Now you require two sets of data. One is parametric test data, and another is a wafer map from the probe yield. Now the multiple analysis uses the wafer map to try to separate the random yield and systematic yield. The objective of the spatial analysis, distribution analysis, is try to find out specific failure patterns or signatures on the wafer map itself to try to identify what kind of problem you're seeing in your wafer. So once you separate the systematic portion of the yield losses, and then you look at the parametric e-test data, then you do a correlation and do a statistical correlation. So the main purpose of this statistical correlation is try to screen out those over 100 parameters, screen out those only significant parameters affect the yield. So once you screen out, you get those parameters critical, identify those parameters critical, then you try to answer the question, okay, what's the actual yield impact of each parametric parameters? That's what we use in the multiple regression modeling. So we try to build a model to modeling all the parametric test data. So after the multiple regression, we can answer all the yield impact, what the effects each yield impact of each parameter. Then we go to the parametric and process module analysis. What we here try to do is try to translate all the parametric problem down to the fab problems. Okay, so the fab engineer can do the root cause fix to improve yield. So once you identify cause, then we can physically improve, generate a yield improvement plan and set the yield expectations. Now next is the detail of how multiple die analysis is due. So as well, we know wafer sort yield is limited by both systematic and random. Now if the yield is only limited by random defect mechanism, so the systematic yield portion will be equal to 1. And due to the random nature of the random defect, it should be distributed evenly with equal probability across the wafer. And the random yield should follow Poisson statistics, which is the yield would be decreased as the die yield increased or the Poisson defect density increase exponentially. Now look at the A is what the actual product, die area, and the D is the Poisson defect density. Now, as what we know, the random defect density, because the random nature is distributed across the wafer with equal probability. So one way we can do that is we artificially increase the die area for a given wafer map. Okay? What we do is clustering the labor die to form a larger area. In this case, we can group by 2 die and form a larger area of 2 area. You got 2 group by 3 labor die would be 3, and 4 labor die would be 4 area. You got 4. Now and then we calculate the yield based on the following criteria. Every clustered die inside the cluster is yielding. Then we call it yielding. For example, group by 2 die, all the 2 die have to be yield. We call it yield. If you cluster by 3, all the 3 die have to be yield. We call it the yielding die. Then you have a set of equations with given different areas and different yields. And then after you get a set of equations by grouping different die size, then you can do a linear fit of the data, okay, to find out what your systematic yield is and what your random yield portion is. Okay, the graph to the right, okay, this, as you can see, this is real data. And then the first point is area equal to 1, and then you go by 2 die area equal to 2, and you have a certain point of yield, and so on and all the way. Now the blue line is here is the theoretical Poisson curve. As you can see, the y sub s, the systematic yield portion, basically is the factor on the yield equation. So the difference between the theoretical Poisson and your real data, this portion would be your systematic yield. Next, please. Now next is I call sort yield spatial distribution analysis. This include a composite map analysis, a stepping field analysis, a quadrant analysis, and a radial analysis. Okay, the composite map analysis mainly just look at the wafer map itself across. In this particular, I have 2,149 wafers stacking together. And the larger the square, the higher the yield with the composite. So want to look at overall the wafer map, is there any particular pattern, failure pattern on the wafer to cause a die wound yield? In this particular, right here, this region is much yield lower than this region. Now, next thing is we want to find out is that do we have any photo repeater defects? okay, either due to physical, the defect on the physical mass or some photo stepper related problem, like a tilted wafer or uneven chop, those kind of things. So what we do is, okay, in this particular case, you have 2 by 2 field, okay, 2 die by 2 die field. Now, in this case, you calculate the average yield of each die inside the stepping field. You calculate the mean, median, standard deviation. And then now, after you calculate, you set the highest yielding die inside the die as your control group. Then you do a statistical comparison, a t-test, between all the die relative to the highest yielding die. Now, if any die, the yield difference, average yield difference between the die is statistically significant, okay, across all the wafers, then you say, okay, yeah, okay, it's probably you have some repeater defects, okay. In this particular, like the die number 1 is yield always, is statistically lower than the die number 1. Okay, the quadrant. Okay, in this case, once you identify all the lots, and then you have the lot general, a list of the lot numbers which have this repeater defects, then you can feed back to the photo engineer in the fab to identify, do some commonality study of, is that all the lot go through the same stepper or same time period or any particular problem to cause this kind of problem, few repeater signatures. The quadrant analysis also is basically similar to what the stepping field analysis is. So in this analysis, mainly you try to look at a specific portion of the wafer has problems, okay, lower than the other portion of the problem. So basically, do the same thing. You break the wafer in 4 quarters, 1, 2, 3, 4, and then you calculate the yield of each quarter and the standard deviation, and then you do the statistical comparison between the higher yielding quarter with the rest of the quarter, and then see any statistically say, yeah, one of the quarter, yielding lower than the other quarter. So you have some kind of failure pattern to identify. Our next thing is called radial analysis. Basically, you try to look at is any radial dependence on the yield on the wafer. What it does is, you look at the wafer breakdown as concentric rings, okay? Now this is center wafer, and then you look at the yield, this centimeter, in this case 0 to centimeter is one area, and then 2 to 3, 3 to 4, 4 to 5, this is what x-axis, but y-axis will be yield. Then you look at the yield across the rings from center of wafer to the edge, you can see the yield roll off. Then you identify, okay, that particular product in this process has radial dependence or not. Next, please. So now this is, after we look at the wafer map, we separate the random and systematic portion of the wafer and look at the wafer map and identify some of the specific failure pattern. Next thing is we want to correlate the systematic portion. Now we can separate the random now. So all the systematic we can correlate to the ET parameter. So this will give you a better correlations. As we know in the conventional correlation, you look at wafer to wafer correlation between the yield and the ET parameter. There are 2 problems associated with it. One is, as what described before, the yield is confounded with both systematic and random. Okay, so you correlate a particular yield, the yield to the particular product. Usually you use hardly to see correlations. Second thing is, the yield could be affected by multiple ET parameters, not only single one. So you correlate a single one to a yield, then you also may not see any correlation. And all the correlation plot is just a scatter plot. Another engineer referred to the famous scatter plot, is what I talked to. So now I developed a specific technique to how to separate the multiple ET parameters effect on the single parameters. So the random and versus systematic, I already do it by multiple analysis. In this case, the technique would be try to separate the data in 4 groups based on the systematic yield portion. Next, please. Now, how you separate each group is the top graph is cumulative probability plot of the systematic yield, and the bottom is the equivalent same data set but plotted as a histogram. Now, each group would be equal to a quarter of the percentile of the data. The higher yielding group 1 would be from 0.75% and to 100%. The next higher yield would be 50% to 75%. The lower yield would be 0 to 25%. Now notice in this graph you have a lot of 0 yield wafers, okay? But this is particular happen because when we're doing the multiple die analysis, because if you have very low yield wafer, most likely all the yield is due to systematic problems, okay? So it doesn't matter how you group them, it's still a systematic problem. So in this particular case, in order to avoid this kind of problem, so I would artificially set that every die less than 2% yield, I would treat it as zero yield. That's why you see a lot of zero yield wafer here. Okay? Now once you break down the 4 group, then we can do the actual, and then we can calculate all the statistics within the groups. Next, please. So basically, next step, after we separate group, then we calculate all the statistics like a mean, median, standard deviation in the quartile range. Next, please. Now here is a sample output. Okay? Now you have 4 different groups, the high yielding group, less, and the lower yield group. And the cost will be all, whatever the ETF parameter is, maybe over some particular, over 300 parameters. Okay? Now you calculate all the mean, the median, and standard deviation, okay, and in the quartile range for each other parameter for the correlation of each parameter to the systematic yield. Next, please. Now, once we calculate all the statistics, then we actually need to do a statistical comparison, do a t-test, okay, between the high yielding group and the lower yielding group. So make sure, want to find out which parameters actually statistically say, yeah, we affect the yield. And we also calculate the correlation between the yield and ET correlation coefficients. So make sure it's a high coefficient, then we can identify that was a yield impact, has a significant yield impact on the yield. Next, please. Now here is a sample output of the calculation and comparison. Now notice there's 2 types of analysis, okay? That one first time we call classical. Second, we call robust. Okay, the classical is basically is compared using the mean and standard deviation to compare the different, to do the statistical analysis. Okay, if the data come from the distribution, normal distribution, and the classical will give you more accurate. On the other hand, if you have a normal distribution of data and all outlier-prone data, compare the mean as create more beta error. Then, in this case, a robust, which compare the median and using the interquartile range number to do the statistical calculations, has more accurate than the regular standard classical. Now, in this case, all the mean and median, and also look at the t statistical confidence level, all go calculated. In this case, you compare your 0.874 versus 0.8789. It will say, yeah, only 79% of chance they say they are different. But however, you look at the next group, 0.76, given the standard deviation or in the quartile range of this and this, and then the statistical analysis will tell you, yeah, 99.9% say, yeah, 0.67 is lower, definitely lower than 0.78. It's statistically significant. Now, after you calculate every single group, okay, now the second thing you have to calculate the correlation coefficient, which is you want to correlate the mean of each group and what's the correlation coefficient, and you correlate the median of each group and what's the correlation coefficients. So you will automatically calculate based on this statistical analysis. Next, please. Now, once we get all the statistics and get the correlation coefficient and the statistical significance between groups, so we can identify those parameters. We screen out those parameters that only have high correlation coefficient and also have statistical significance between groups. So those parameters will be considered as yield limited factors. Next, please. Now here's a graph to show you how effective of this statistical correlation is. Now in this top left graph, okay, the x-axis would be a particular ET parameter, and the y-axis would be the yield. As each individual point is individual wafer. That's what I call conventional analysis. You look at the wafer-to-wafer correlation. In this particular, is partly CD. As you can see here, it's hardly see any correlations. You can make any statistical conclusion out of it. You have correlations. And you look at the cumulative probability plot, basic distribution of the ET data. As you can see, there's about 30% of the data outside the spec. But when you do a correlation, you still cannot conclude that, yeah, outside the spec, you have lower yield. But however, now let's look at the statistical correlation. Okay, this is given the same data set. Just recalculate. Each point is average, or mean or median, depending on the statistical analysis, the data distribution is. Now each point is the average of each quartile, as I described before. Now, as you can see here, once you break it down, remember, this graph already shows you each point is statistically significant, different than the high yielding group. And when you do a correlation, you get really high correlations. Okay? Now, this graph is a cumulative probability plot of the same data set for different groups. As you can see, the high yielding group has much significant data point less, outside spec than the lower yielding group. Next, please. Now, so far we already go through the order analysis. We already identify the critical ET parameters which affect yield. The next question the answer is, okay, now what's the actual yield impact? How many die we lose due to particular ET problems? To do that, I'm using a multiple regression modeling technique. What multiple regression modeling technique is, try to build up a mathematical functions to relate what your systematic yield and what your input parameter, in this case the ET parameters, what you find out is. But before we do the multiple regression analysis, okay, for ET parameter, as we know, all the ET parameters will be maybe interrelated and not necessarily independent. But multiple regression, you need to get the parameter as independent as possible. For example, the ET, when you test the ET, okay, you find that VT has a significant yield impact, okay, your transistor VT. Now we also you find the drive current also has significant yield impact. And also you look at L effective, you also look at significant defect. But you look at overall, the three parameters all related to transistor design, right? So all you want to do first, you want to go to multiple analysis, you have to apply your device physics knowledge to identify, okay, now for the particular sample I give to you, you should pick the drive current as one of the ET parameter as your transistor module problems, okay? And so forth, and then you identify all X is what the ET parameters. And then you have some constant and the coefficient of each, this is linear term, square would be the quadratic term. And also if you can put some interactions between parameters to put in your model. Now once you build up the model, then okay, first you calculate all the coefficients, right? The K's, the A's, and B's, and interaction coefficients. So once you calculate it, and then you do an analysis of variance, what it does is, okay, which parameter in the model is significantly can explain, okay, what the yield variation is, okay? Now some of the parameters may not affect your yield equation. Then in this case, you can eliminate them, so you can much, better accurate, or you're simpler, in other words, simpler model. So you do it one at a time, so you eliminate one of them, which is to show you is non-critical, then you recalculate coefficient again and do the analysis or variance again. So until you do the multiple loop and then find out what satisfies, okay, your multiple model. So once you satisfy find the first model, then you can start and calculate the yield impacts. Next, please. Now once you build up the model, the first thing is you want to look at the main effect, okay, of each parameters to the yield. Okay, so but what a main effect is basically look at the slope of your ET parameter and your yield is. In this particular case, for this parameter, number one, you can from low to high. In this case, you have lose 53 point die per wafer in this case. Okay, now because the slope, so only the magnitude is counts, because right here you look at what the delta change in the input and what your delta for your response is. So by ranking those parametric parameters, then you know in your process which critical process parameters need to be better controlled, because small change in your input, you could have significant yield impacts. That's what I call the fab process control. Okay, you need a better control on those fab parameters or ET parameters and translate to the fab process module control. And also in this case, you also provide you the 95% confidence level of the slope. Basically, telling you the range of your slope is. Next, please. Okay, next is the sample output is, okay, once you identify which parameter has sensitivity, where is, need to be better controlled, the next thing we haven't answered is, okay, what's the actual yield impact for that particular parameter? Okay, now the next thing is, okay, to answer that, first thing, we already build up a certified model. Then we do an optimization step. What optimization step is, you try to find the optimum setting, okay, your input variable to give you the maximum yield. Okay, so basically you do optimization, using a computer program to optimize your yield. Now, after you go through the optimization step, then computer will give you optimal setting for each parameters. Okay, so if you're running at this optimal value, you should get your maximum yield. Okay, now you go back to look at what your process is. Okay, what your process means is what you're currently running. In this particular case, optimal value 0.6, and then you're running 0.67. Because you're running off the optimal value, you're losing some die. That's what so you're losing some of die because you're not running it. Okay? You look at second problem. Okay, you assume all of other processes running optimal, and this one is not running optimal value. And what's the die losses? So you rank them, okay, by order all the parameters. Then you know each parameter what the die actual yield losses due to that particular problem running off the optimal value. Okay? Notice that, okay, the ranking for the yield loss and the ranking for the need to better control is not necessarily the same. Okay? So the higher yield loss may not have higher sensitivity or vice versa. Next, please. So, okay, the next thing is, okay, once we identify the actual yield loss, we want to find out, okay, where's the possible cause? Okay, we do all this kind, we do the analysis distribution, we do, checking design rule, and to find out, we find out is the process problem or design problem, or the e-test limit problem, okay? And also we look at the process capability, okay, see is that the possible capable. And also, once we look at the parameter, ED parameter, particular problem, we want to translate to the fab problems, okay? And for this instance, if high contact resistance is one of your e-test parameters, to be considered as critical to the yield, and then you will see that some systematic yield loss due to the high contact resistor, then you will go back to look at what the fab process module associate, okay, with that e-test parameter will cause. For instance, it could be a contact CD problem, could be your contact pre-clean or contact edge problem, or could be your uniformity, edge uniformity problem, or could be your metal step coverage problems. Next, please. Now, once we identify all the e-test parameters which have significant yield impact, and also we know what the actual yield impact is in terms of die per wafer, then we can focus on the top 5 problems, okay, to generate a yield improvement plan, because we know all fab is resource limited. So we want, you look at list of problems. This is the top 5 problems in a particular fab, and then these are what possible fab process module cause problems. In this case, we can set the yield expectation by fixing the top 5 problems. In this particular case, you will recover almost 87% of the yield by just fixing the top 5 problems. Next, please. Okay, conclusions. Now, I already described fast. I described the parametric analysis methodology. This parametric analysis methodology, could be from over 100 parameters or more, and can be after the analysis will be translated to top 5 problems in your top 5 parametric problem in your process, and also is capable, okay, from translate the parametric problem back to your fab process module problem, and so we can fix the root cause, okay, and also we can set the yield improvement plan based on the analysis of the parametric analysis. Also, we can set the yield improvement expectations. Okay, after you fix the problem, what kind of yield you should be seeing. And also, this methodology can separate and quantify systematic random yield losses. Okay, and also this analysis definitely put a lot of emphasis on statistical analysis techniques. Okay, and also it's fast. Fast because we already developed a software to running all the analysis, okay? For looking at 2,000 wafer, if you look at all the analysis, it usually takes weeks, and then right now we can down to less than 2 days to get all the analysis. Okay, so overall, this is effective and fast and very comprehensive parametric analysis. The last thing is we can use as fab yield evaluations. Next, please. Now, the parametric analysis are developed, okay? First thing we can do is we try to look at the yield evaluation on your fab. Okay, we try to understand what your systematic yield loss, what your random yield loss, what your yield opportunity is. To do that, so first thing you can look at the multiple analysis. Okay, try to quantify what's systematic random. And you look at perform spatial analysis, look at, okay, what's the failure pattern and so on. So once you identify systematic and random, there's a different approach, okay? The approach I'm just talking about is, okay, now how you find out the systematic yield sensitivity factors. And later on, you can generate a yield improvement plan, how to fix the yield and what the yield expectation is. And in other words, doing a fact evaluation, you can also evaluate what the actual random yield loss is. To doing that, you can measure the equipment defectivity. Okay, we measure equipment defectivity, and also we compare the particular fab data with our database, okay, benchmark data in our database to look at what your equipment defectivity against rest is the industry. And also we do a focus search. Okay, we look at process-induced defect. Okay, we do a different scanning of the step to look at what the particular process-induced defect is. And overall, you also evaluate what your random defect reduction methodology and help the customer to get a fast yield learning rate. And I will conclude my talk.
Well, I think we'll have time for about one question before they start kicking us out of here. Yes, please.
How sensitive is your software to the number of wafers tested? What's the minimum number of wafers that you need to run this on?
If you look at, because the statistical point of view, you need the multiple lots, okay, to look at lot-to-lot variations. And then you can do by single lot and with a single wafer, but when you look at the statistics, compare the stacking map and all those fields, I would say, at minimum 3 lots.
And how sensitive is your model to the case where you have very low yield in the fab? What if you're averaging 20% yield and you try to run this analysis?
We haven't tried the 20% yield scenario, but we tried the 40% yield. 40% yield, we tried it, but it's very effective. But 40% yield, most likely you will find that a lot of systematic, parametric problem. But you're looking at 80% yield or above, you look, differently. The distribution of systematic and random is different.
Okay, thank you very much. Before we break up today, I have a couple of things to say.